My name is Peter Manev, and today what I'd like to share with you is a couple of things that we've done, who we are, and how we've done them, and challenges that we've seen in terms of working with Suricata in particular. So talking about Stamus, I do see, IDS, get the feeling. So our talk will be about Suricata. Better, faster, and stronger, or how we're doing it with the Suricata example. So the agenda, as I mentioned, a quick introduction of who we are and what we do, a quick introduction of Suricata, the traditional challenges that IDS and IPS systems face, including Suricata, and our experience with it. So about me, my name is Peter Manev, as I mentioned before. We co-founded Stamus Networks with Eric LeBlanc. We are both part of the Suricata core team. I'm a PEVMA on Twitter. And the idea kind of came in naturally because people just kept asking us for, hey guys, can you help us with this project or that project? So it naturally came up, and 2 years ago we started doing that as a commercial entity. And we did create on the 1st of April. My mother said, I don't know whether to laugh or cry, but just so it happened, the paperwork hit that date anyway. So what we do is hardware and software appliances, central management for those, customization, architecture services around Suricata, any custom code features and things like that. Everything that we do is Suricata-centric and built around Suricata and for Suricata. Of course, and we're very, very, very open towards and contributing towards open source. So talking about Suricata. Suricata is an open source software on the GPL version 2. The code is owned by a US-based non-profit foundation. In other words, the non-profit foundation cannot be bought and the license cannot be bought, so that was the main purpose of it, keep it actually free and open. Suricata is very much open about anything that it has in terms of bug features, documentation. Everything is open to the public, and anybody can come in, report a bug or report a feature, or actually even if you want to donate code or discuss with the team. It's very community-driven. There's public roadmap discussions, and we do kind of Suricata conferences once a year too. So we try to be as much open as possible to anybody that is willing to use it, contribute, help, and all that. We're, of course, problem-fixing oriented. We also have 2 open source products that are on GitHub, and you have all the links at the end of these slides here anyway. So we have Selks, which basically is Suricata, Elasticsearch, Logstash, Kibana, and Sirius in all-in-one distro. And then the Sirius is the open source graphic-based rule set manager for Suricata. So again, we try to give back to the community as much as possible from the Stamus perspective anyway. So through Suricata, we offer like automatic protocol detection. So for example, for HTTP and similar, you don't need to specify which port you expect to see HTTP on. Suricata will automatically detect that. It could be port 62,000 something, it doesn't matter. You have also a lot of metadata extraction. In other words, and we'll show you further, as we go further down the slides, a couple of examples what we mean by that exactly. So it's further supplemental info to the alert that you're getting in order for you to make a better judgment on that particular alert. Extra information in terms of, was it an HTTP, was it through SMTP, a TLS, any extra info that we have, we'll add it in. I can also do file extraction at the moment via HTTP, SMTP, and NFS version 2 protocols. And there's upcoming work on FTP and SMB. So there we can extract files and then post-process it, and give you the opportunity rather to post-process via other tools. So the difference in what the difference in what we're doing is that these 4 major points, and we'll talk about that as we further move along with the slide. So Suricata, Rust, metadata, and expertise. All the combination, in the combination of those 4 rather. So talking about metadata, and there's 2 types that we will cover. For example, this is a supplemental info to an alert. And in this case here, you have extra information about that alert in terms of extra HTTP metadata. In other words, user agent device, in this case it's Huawei, HTTP referral, HTTP user agent, and things like that. Extra information that is available to you when you look at an alert to make a better judgment. Same with, for example, in this case is HTTP response body. And in this case, it's actually a Debian package. So you have the actual Debian binary executable inside the response body. And we have the response body as a, you can create a packet, if you will, in Wireshark out of that. So that's the type of extra metadata that we're talking about when you're looking at alerts. So in other words, you don't just look at source and destination IP and the name of the rule that created it, but you actually have some extra info like that that you can act upon. User agents, response body, the whole lot of it. GeoIP information if it's available too. Same with DNS, a bit of DNS extra metadata to that alert in order for you to make a, pardon me, a better call. Also, this is like in a JSON format, so it's easily pluggable into any database, and you can further on do filtering or selection as you wish. It's very, very, very powerful. And so you can have, for example, an alert event like that. On the top, you'll see the alert itself, actually, the signature category and similar. And on the bottom, you'll have a little bit of more supplemental data to that alert, the extra HTTP metadata, the extra GeoIP metadata, and some flow info. So all that combined. So actually, you wouldn't be looking just at the top part. You'll be looking at all of these. And that's where Suricata actually allows you to have a better visibility, better understanding of why did that alert happen, or any supplemental info, as I mentioned, to make a better call on it. So talking about Suricata, it's basically multi-threading IDS, IPS system. It has native IPv6 support. It has different modes of operation. It can have hardware acceleration. Just to give an example, Napatech. So it can be used as an intrusion detection system. It can be used as an intrusion prevention system. There's a hybrid mode, IDPS, in which we just set reject packets to reset the session. It also could be used as just a monitoring tool. In other words, you have just a, Suricata is not doing any active inspection, but it logs everything that it sees. So in other words, it will log HTTP, DNS, TLS, all those things. It will just log them without doing any inspection. It's very easy in terms of performance on you. We can do file extraction, JSON logging standard, as I mentioned before, so it's very easy to plug that into any existing DB or analytic systems. NetFlow SMTP support, we have the possibility to hook up your own Lua scripts into the rules. So in other words, whatever you can do with the Lua programming language, you can write a script and say, whenever that rule triggers, make sure it triggers the script as well, and you can do a bunch of post-processing stuff on it as well. Very helpful. Also performance consuming, but helpful nonetheless. So further on to add in IP list, reputation, GeoIP, all that is some of the major things, that features that are available in Suricata. So in 4.0, which is the current stable, some of the improvements that were in there, we included Rust, and we're going to talk about that in a second. File extraction from NFS. A big rework on the streaming engine in terms of performance and accuracy. We added a bunch of new keywords that are to be used with rules. One of them is target. the target keyword, and I'm going to show an example of the usefulness of it in a second as we move down the slides. And of course, increase ability to provide metadata output to Kafka. That's totally new for us in 4.0. So some of the traditional problems with C, Suricata inspects the network traffic, so inspects anything that goes on that line, and that could be a lot of things. Suricata is written in C, and as we know, C deals directly with mem allocations and similar. So if not done correctly, you can segfault, have mem leaks, and much more. So a bunch of things can go wrong, actually. And this is where Rust comes in to help, and it's new in 4.0. So Rust is a programming language that allows us, Suricata actually, to fail properly, if you wish, or to better fail. So it's blazing fast, prevents segfaults, and guarantees thread safety. So in other words, it solves out of boundary data problems, buffer overflows and similar. It solves that problem for us, for Suricata. So it's a project created by Mozilla. We currently introduced the Rust parsing for DNS and NFS parsers as well. So it's rather new. We will keep adding in more protocols to it. But this was the first round. So there's a learning curve as well, including to C developers. But it's something very powerful and provides extra security and robustness for Suricata. And as we do inspect everything that's thrown at us on the wire, it goes a long way. So the idea of Rust was actually introduced by Pierre Schiffler. He had a talk at Suricon last year, securing the security tools. He helped us a lot in terms of implementing actually that into Suricata. It was a lot of work, and there's a lot more coming up, but good because we're moving in the right direction, I think. It uses a protocol parser called NOM to ease development and for better security. So far, that's a new thing for Suricata and very helpful. So talking about another aspect of the metadata, here is an example of a rule for Suricata. So Suricata is a signature-based engine. It inspects the traffic it sees based on rules. So you have to tell it what to look for. In this case, here's a simple SQL rule. And one of the traditional problems, and I was talking about that with Eric actually, just over breakfast. One of the traditional problems that we have with alerting on these rules is actually what is the actual source and what is the actual target. So as you see here, you have alert external net to home net, but what is the actual source of the attack? So you can actually, we introduced something called target, and I'll show you how that is helpful. So for example, imagine you have a CNC beacon from your internal network. You have a compromised machine that sends a beacon to the master server, to the command and control channel master server, and says, hey, I'm available for update or for next commands and things like that. And if you have the traditional rule alert home, from home to external network, that would actually say source and destination IP inside that alert. But the real target of the attack is the one that is sitting inside your internal home network. So in the JSON output, we can add in another record on the bottom. Actually, they're saying target. And we can specify via that keyword target. The target is the destination IP or the source IP. One of the two, you have to choose one or the other. Pardon me. So we can add that extra metadata in there. As we add it in, this is just another piece of data in the log file. But the log file, in this case, as being JSON, is very easy, as I mentioned, to plug it into your analytical engines and search on it. So you can go from graphs like that to graphs like this just by doing filtering. This is basic filter search on Kibana on the target keyword. So in other words, you can go from an approach like this. Let's try to figure out what happened to an approach like this where you say, aha, okay. We can clearly see what the targets are and just click in and see, and that will hopefully save you like 1,000 dev hours on the analytical team and similar like that. So that's one of the improvements in there as well. This has to happen on the rule level itself. In other words, the rule has to have that extra keyword in there specifying. But you can select your top 10 or 50 or 100 rules, and if you're interested in coming up with a graph like that, it's very easy to actually pinpoint places, problematic places. Now, when it comes to performance, the major performance factors for Suricata, any intrusion detection system, any intrusion prevention system, the first biggest impact is actually the rules. I know we're talking about 100 gigabit a second, 10, 20, 50. You can have the same hardware performing better on 20 gigabit a second than 1 gigabit a second, for example, and that difference can come from the rules. In other words, if there's a badly written rule, or if the stuff that you're looking for is more performance intensive, it will have an effect on the overall performance. So it's not only about hardware and speed, it's also about what you're looking for and how you're looking for it. So IDS, IPS systems, they need to look in the traffic and make a decision on that. So it's not just about 1 million packets per second, it's about, let me see what's in those 1 million packets per second and do the inspection as you wanted me to do, or look for that content that you needed. Then the other point that affects performance is the Suricata version use. The Suricata is a very dynamically developed piece of software. We have frequent updates, features integrated, and things like that. So bug fix releases and all sorts of things. So stay current, please. So the other part that affects the performance is the hardware and the operating system that you're using, of course, and the type of traffic. And when I say type of traffic, by that I mean there's a great difference when you're doing IDS or IPS on a university network and when you're doing that on an internet service provider level. Because on an internet service provider level, everything is shaped up and they have much more controls before you see it. But in a university network, campus, it's my favorite networks, anything goes, anything flies. So if you survive that network, you probably survive any other. So the OS challenge. So we have different OSs that they're all the same, but they're not. And different kernel versions, you have different NIC vendors, you have different driver versions. So all those things do have an impact, and you need to stay on top of it most of the time. So generally, on a commodity NIC, here's what happened to my packet. The packet comes in, usually the NIC takes it, puts it into a RAM ring buffer, the RAM that's on your machine. Then an RQ is raised, the driver wakes up, clears the RQ, and sends it to the new app, the networking app, the new app. So that's usually, in general, the flow there. And in our case, for Suricata here, in one of these examples, this could be, so when it goes to the API, this API could be, for example, AF packet. AF packet is the Linux native packet acquisition method. So works out of the box on any Linux kernel above 3.1. It has load balancing functions like flow-based, CPU-based, RSS-based, and then we have the enhanced BP filter-based as well. So there are things that you can do there. But so for example, this is Suricata running in workers mode. So as you see here, we have RX queues and then we have threads, and each thread is pinned to a CPU. So the capturing part, decoding, streaming, detect, output, all that needs to happen in the same, or it's happening actually in the same thread. One of the challenges that we see here is, for example, when you have the so-called elephant flow, somebody downloading a Blu-ray DVD or watching Netflix or similar things like that, it will peg that CPU while others won't be busy. So that's one of the challenges that we're looking at. But there is also another challenge that actually, as I mentioned, Suricata is IDS APS, an IDS IPS engine. So in order to make the best decision for what it's built, it actually needs to see all the packets in the correct order in the same thread. So the RSS scaling is actually made for big web file servers. It actually can distribute the same connection over multiple CPU cores, and that's good for their perspective, but not from our IDS perspective. So we need to see the packets in the same order, in order, as the client would see it, in order to actually inspect the traffic the very same way the endpoint would receive it to make a best decision on it. And in this case, we can end up in a situation where the packets will arrive, Suricata will see the packets out of order, won't see the three-way handshake or things like that, and it will not consider that flow, for example, valid. So this is a big challenge. Solution to that is, on a commodity NIC, for example, a solution to that would be to force one RSS queue, just manually force it. You just sacrifice a CPU that is just going to do that. In our test, the limitations were with Michael Purzinski. We wrote a paper actually called Septune, where we did some tests on a 20 gigabit a second line. And that was one of the things that we tested. We used only one RSS queue, and we figured out that it can handle up to 2-3 Mbps. Another approach would be to use multiple RSS queues, but that requires the kernel version bigger than 4.12, some patch drivers, and you need to manually set the RSS hash key with a low entropy value. So there's ways around it, but it's much more administrative intensive. On Intel NICs, the 510, the XL510 actually does not have a symmetrical hash, so the only option there is to force one RSS queue. In the 710, you can do it. The hardware is there. The driver doesn't allow it. There is a patch proposed by Victor to be accepted, but I don't know how far that has gone in. Or in our experience and tests, as we saw, you can always, another solution to that problem would be to use a card like Napatech FPGA or similar. There are some Linux improvements, some of them that have been around for a while, some of them are very new. So the first one is the enhanced BPF. It's actually an improvement over the classical BPF in terms of that allows you to hook up your own scripts. It opens a lot of doors for Suricata in terms of performance, for sure. It opens the possibility to deal with kernel, with elephant flows in terms of bypassing those. The downsides is that you need a really good set of expertise to understand eBPF and to write your own scripts. So it's not so easy as in terms of just switching it on and off. You have to write your own scripts for it. A newcomer in the Linux world as of this year is actually the express data path. That's what a couple of the guys like Dave Miller and Jasper have been working on this year. And Jasper Brewer, if I pronounce the last name correctly, I think he's based in Denmark anyway. So this is something very, very, very new in the Linux kernel, introduced in kernel 4.12. So it has no specific hardware requirements. It offers bare metal packet processing. It's not a kernel bypass. It offers like an integrated fastpath in the kernel stack, programmable as well. So it looks very promising. As I mentioned, not exactly a downside, but it's literally a newborn baby. So it's very, very new. to Linux. But I think they're working very hard on it, so we should expect some results soon. Eric is actually actively working with the folks doing the XDP to make a Suricata patch and test it, so we can test it out and see how it behaves and what we need to add in and improve or have any future requests. So the traditional high-speed challenges of intrusion detection, intrusion prevention, and all that, including in actually the live testing that we've done, is NUMA node controls. So that's very important. The packet acquisition, OS, NIC drivers, versions, dependencies, as I mentioned before. We need to fight the elephant flow. So for example, we don't care about, from security perspective, we don't care inspecting that Netflix session. We don't really care about that video conference streaming that is going on. So instead of actually continuing on inspecting it, we would like to bypass it. We're not interested in that particular case, for example, at that anymore. So it will save us a lot of power cycles and CPU cycles as well. Packet reordering, as I was mentioning, the RSS problem and the asymmetric hashing. So the commodity NICs that are sometimes a good cheap buy, they don't handle very well above 10, 20 gigabit a second, so you need something much better, fit for the purpose type of thing from an IDS, IPS perspective. So as we move along, 40 plus gigs, because Suricata, we are aware of a few installations that are 40 plus, on the 40 plus pipes with Suricata. So when we come to those speeds, and especially having in mind the points that I mentioned before that have a huge performance impact on IDS and IPS, so you need some advantages that the FPGA offers. So for example, like flow bypass on the NIC level itself, that helps a lot. Packet merging that guarantees packet ordering. So we need to see the correct packet order. Minimize the pressure on the PCI bus. So a lot less CPU cache load misses and that stuff. You have also some packet filtering classification capabilities. All that helps a lot so that we can inspect only the traffic that we need to inspect, to not everything else. So we did some testing with a Naptech card on 100 gigabit a second, with 100G pipes. We had 2 cards in 2 NUMA nodes. The setup was 2 cards with 2 NUMA nodes. The advantages there that we saw from Suricata's perspective was per queue buffers. You had a very good NUMA control and setup. We didn't need to worry about asymmetrical hashing and things like that. We also didn't need to worry about packet ordering and in RSS multi-queues, like kernel versions and things like that. We didn't have to worry about that. There was no, the hit on the PCI bus was not that high either. And this was a huge speed. It was done against like a PCAP replay, but nonetheless, I think we reached something like above 90 gigabit a second, which was like, wow. For me, at least, I've never seen 176 cores on H-top, I haven't seen that, so I saw it with that, and the effect was like, okay. so that was good. So, yeah, this is definitely where the advantage comes in. So, the advantage that we saw from Naptech was actually they were very open to open source. I have 2 people to thank here, Peter Sanders, thank you, and Philip Young, I don't know if he's in the room, but they actually work with us, and they actually did a PR, a merge request, so we did improve a lot of the statistics from Naptech card into the output logs of Suricata, so that helps Suricata a lot, and all Suricata users. So very open to working with open source. So that helps a lot. And the wish list, I'm not done yet. It's going to be a while. We have a wish list, but this is just number one, okay? So hopefully the wish list is flow bypass on NIC level, as we mentioned before, so we don't even have to look at it from Suricata's perspective. We don't even have to look at that anymore. We just say, we're not interested into that. Get rid of it. I don't want to say it. So that will help us a lot. And I think that's really it. A big thank you. You have all the references in the presentation itself, so all the information is there as well. I'm open to any questions, please. Eric.
See if I can find my question. The flow bypass thing. Yeah, so, I mean, you have the NTQL, NTPL, I forget the name now. You have that ability to apply the filter based on what you see. What is it that you're looking from Napatech? Because I thought Suricata would be the application that tells the Napatech card to apply this filter for this session until I say to take it off. So what is it that you were asking for?
Well, what will help a lot more, it would be like, pardon me, some way manually or dynamically, hopefully, to set up that and to say, and to say, hey, this is Netflix, I don't care about it. Hey, this is a huge torrent download. I don't want to see it. It's just, I don't want to see it. I'm not interested in it. So instead of all that coming to Suricata and Suricata looking at it and say, oh yeah, that's the stuff that I didn't want to look at. Okay, now, all those cycles, it would be a huge performance.
So what you're looking for is the Napatech to do DPI of some sort.
Something like,
okay.
Something like that, yeah. We need to sit down and figure it out, but
cool.
It will help a lot, yeah.
Thanks.
Because your network inspection from, for example, 10 gigabit a second will go down to 5 or 2, because you're not inspecting all video streams, you're not inspecting all YouTubes, you're not inspecting Netflix and all that stuff. So it's a lot easier. Please.
So basically, what did Eric make with the kernel?
Yeah.
Flow bypass.
Yeah.
It's basically the same feature you want to have implemented just on a NIC level.
Similar, yeah. But what we have implemented at the moment as a flow bypass is not as fast. So, and instead of us coming into us, and as I mentioned before, Suricata looking at it and say, oh yeah, that's the stuff that I really didn't want to look at. Let me not look at it anymore. Yeah, it will get much easier.
But the flow bypass that Eric has made, looks at the first session of the packet, of the first part of the packet, and determines, okay, this is something that is not interesting, and then it tells the Linux kernel to discard it for you.
Yeah. Exactly.
So you want something more intelligent than that, or do you still want to see the first? Because I think you want to see the TCP handshake still, and then from that point on, you want to discard the flow.
Yeah, that too. But this is something that we actually need to sit down and figure out exactly how we want to do that, because there's a lot of possibilities and ways, and I'm sure you have ideas that we haven't even thought about from our perspective as well.
Yeah, because I mean. Today we have the possibility of going in and deleting certain flows. Based on so basically implementing what Eric has done on the kernel level. That would be easy to implement, but a more
sure. But that would be a great
advanced version. I would definitely.
Yeah, sure. That would be a great start right away.
Yeah,
sure. Please.
A very low level one, 100 gig. How much do you see it demand? 100 gig. How much deployed? What do you use to generate your 100 gig PCAP files to test in your own development environment?
The PCAP files, Pete, what was it? I have to kill you if I tell you. Yeah. Yeah, the PCAP files I think were public anyway, so we just kept replaying that. That doesn't give you the same level of a real data, if you will, as it runs on the real network traffic. But it gave us a very good perspective. How much is 100 gigabit a second needed? I thought it was not needed as much, but then we had 2 years ago actually. We sat in a meeting with a bunch of guys from F5, and they were interested actually in IDS IPS that can sit around the load balancers, which will do in terabit a second. So I think the interest is, there is no interest because the technology, the capability wasn't there, but now it's there. So as soon as all that is available, I think there'll be more and more interest to be plugged in. Any more questions? Okay, cool. Thank you.